Hi, everybody. It's Professor Mitchell, continuing with Chapter 3. Now we are going to look at measures of variation, 3-2. So variation is the single most important topic in statistics, so this is the single most important section in this book. Ooh. All right, so the three different measures of variation that we're going to talk about are range, standard deviation, and variance. These statistics are numbers, but our focus is not just on computing those numbers, but also being able to interpret them. Okay. All right, so let's start with the range because that's the easy one. Oh, let's start with round-off rule, actually. So the round-off rule for measures of variation is the same as it is for measures of center. One more decimal place than is present in the original set of data. Okay. Just like mean and median. Okay, so your range, all that is just the maximum minus the minimum. What a measure of variation is supposed to do, this is something they could have talked about under the key concept, is how spread out are your data? Okay, are they all over the map or are they within just a few, points of each other? All right, so the easiest way to do that, it does not take into account every single value in the set, definitely, but it's the fastest way is just do the maximum minus the minimum, and that's called the range. Okay, maximum minus minimum. All right. Properties of range. The range is not resistant because, again, just like the mid-range, it is extremely sensitive to changes in the maximum and minimum values. Okay. And because it uses only the maximum and minimum values, it doesn't take every value into account, and therefore it does not truly reflect variation among all the data values. Okay, so here's an example of finding the range. These 5 numbers probably look really familiar to you. Same ones that we were using a lot in 3-1. Find the range of these 5 Verizon data speeds, which are in megabits per second. So very easy, you just find the maximum, which is 55.6. You find the minimum, which is 14.1. The difference in those comes out to 41.5, but I'm going to report it as 41.50 using that round-off rule. Because these data values all end in 1 decimal place, I'm going to report the range using 2 decimal places. Okay. Okay, the most common measure of variation, and it does take into account every single data value, is the standard deviation. So without getting too specific right now, the standard deviation is a measure of how much data values deviate away from the mean. Okay. There are 2 different notations for standard deviation, depending on whether you're working with a sample or a population. Sample standard deviation is denoted by S. Population standard deviation is denoted by the lowercase Greek letter sigma. So you may remember from the last section that an uppercase sigma looks like this, sort of. That has nothing to do with lowercase sigma. This uppercase sigma means add. It's an operation. It's not a variable. Lowercase sigma means population standard deviation. Okay. So here are your formulas for standard deviation. Both of these formulas give you the same thing. In the first example, I'm going to use this first formula. But then, believe it or not, even though this formula looks more complicated, it's actually a little easier to use. All right. So we'll show you what that looks like after we do this one. Okay. So what this is saying to do, there's quite a bit going on here, is first find the mean of the sample. Remember, that's what X bar is. Subtract the mean from each and every data value, and then square all those, add them together, divide by n minus 1, and then at the very end, take the square root. Okay, so that's a lot of stuff. All right, so let's start looking at how that works. It's really not that bad once you get the hang of it. All right, some properties of the standard deviation. It's a measure of how much data values deviate from the mean. I think you heard me say that before. The value of the standard deviation is never negative. And that's because really the way that you get it is by adding up a bunch of squared numbers. Remember, squared numbers can never be negative. Okay? And the only way the standard deviation can be 0 is if all of the data values are exactly the same. Larger values of S indicate greater amounts of variation, and smaller values of S indicate less variation. Okay. All right, and then continuing with properties. Standard deviation can increase dramatically with one or more outliers. Units of standard deviation are the same as the units of the original data values. And then finally, the sample standard deviation S is what's called a biased estimator of the population standard deviation sigma, which means that the values of the sample standard deviation S do not center around the value of sigma. Okay? And that's getting a little bit more technical probably than we need.